This is a production of Cornell University.
So welcome to a Hort seminar. This is, as Marvin indicated, this is, I just finished my my dissertation, as the title indicated, and the whole spectrum of things I did are this. I had 5 different chapters, and today, it covers the past, the present, and future. But today, really going to be focusing on these 2 chapters. I'm not going to be going into everything, but if you do want to know more, I'll give you a brief overview of the other chapters, and if anything piques your interest, please feel free to reach out. Happy to talk to you more about that. I'm going to be talking about some specific field experiments done with hazelnuts and chestnuts today. And this overview of all the nuts that are native to the Northeast. So one of the reasons why I was really drawn to nuts is that they are plants that have been in this landscape for thousands and thousands of years. And in that way, they offer a lot of ecological adaptations that are well suited to this region. And most of the nuts come from oak trees, many different species of oak trees, which have been in this landscape for about 12,000 years, according to pollen records. Also, hickories have been in this region as far as 8,000 years, going in Western New York, according to pollen records. American chestnut was first found at latitudes of 42 degrees north, 6,000 years before present. Walnuts, so we have 2 different species. There's a black walnut, Juglans nigra, and the white walnut or butternut, Juglans cinerea. Those have also been in this landscape for thousands of years. The black walnut having a very interesting sudden peak in its pollen, what would you call it? Pollen signal as early as 500 years ago. So lots of recent interest in that. There's also 2 species of hazelnuts that are native to this region. And of course, the American beech. So there's a huge diversity of nuts that are available in this area that have been here for thousands of years. So part of the research that I engaged in was really trying to figure out what is the history of people using nuts in this area, going back through all time or deep time as far as we can go. And in order to answer that question, I looked at ethnographic records. These include, here's just one quote from Arthur Parker, who was an ethnologist, and also Seneca himself. Seneca are one of the nations in the Haudenosaunee Confederacy. And so this quote reads that nuts were an important part of the Iroquois diet. Iroquois is another word for Haudenosaunee. It's more antiquated, not really used anymore, but great quantities were consumed during the nut season and quantities were stored for winter use. The nut season to the Iroquois was one of the happiest periods of the year. So one of the really interesting things that we see a lot of quotes like this portraying lots of really high energy and enthusiasm for nuts. And then also, however, that's contrasted with what's found in the archaeological record, which is a lot of the archaeologists will write minute quantities of nut fragments, which suggests that the rich source of oils and nutrition from harvesting nuts was not important to the occupants. So there's a really conflicting different kinds of reports coming from different kinds of evidences. And so the first chapter of my dissertation is really trying to untangle this discrepancy. What's going on? And in order to, I developed a hypothesis, and in order to kind of see through this, I found that historical ecology was a really important source of information. And I looked at a variety of different sources, which really indicated that Haudenosaunee peoples were managing forests in ways that what we see is that increase the abundance of nut trees in the landscape. It's called being hyperdominant, much more than they should be. And these are just a couple of figures from these kinds of papers. But here we have in Western New York, evidence of intentional oak savannas where there should not be. These are areas where we have oaks separated from each other by some distance, growing in grass. And then this is also a map, a map of fire-mediated landscapes. This is also in the very same, so here's like that little dip in Lake Ontario shoreline, same thing right here. And then this is Cayuga Lake, and this is a map of canopy disturbance and how that links up with all these dots are locations of different Haudenosaunee settlements and agricultural sites. And so this is just a really brief overview of different kinds of evidences I considered in piecing together the story. This is not the main part of this topic. The main, you know, the moral of the story is here that the forests were being heavily managed, and as a result, nut trees were being increased. And this is really not that surprising if you consider that kinds of evidences, very similar kinds of evidence happening all across really the world. So there's other papers coming out about this that happen in the East, in the Pacific Northwest. There's a lot of recent research showing indigenous management is still, the echoes of that are still measurable in forest communities today. And this has also been seen in the Amazon. Parts of it are giant food forests, and also in parts of Asia. So historical ecology has been a really important and exciting field for me to look into. And if you want to learn more about what this was about, please reach out. Another part of my research was doing community-based work with contemporary Haudenosaunee people. I worked at the Skarure or Tuscarora Nation, which is in Western New York, about a little bit north of Niagara Falls. And so one of the primary questions I was trying to ask there is, what does sustainable agriculture research and education look like with contemporary peoples in a way that addresses not only this historical ecology, but also works with reconciliation in mind and trying to really do justice towards relationship building. And so this was, when you enter the nation, there's a different language. I'm literally in a different country, even though it's New York State. And there are learning about research protocols that are based off of treaties that have been signed. Like this is the Turo Wampum. This is considered a very important treaty that was originally signed between the Dutch and the Haudenosaunee. And this relationship was transferred to the English. That was the whole point of the Canandaigua Treaty. Commemorating the Canandaigua Treaty is coming up November 11th. But what this represents is that these two purple bars are symbolizing Haudenosaunee canoes and white European ships going down the river of life in peace and prosperity, side by side, not interfering with one another. And so if you are interested in working with Indigenous peoples, it's important to know that as a result, like, we are also treaty people. We have roles and responsibility if we want to be building relationships with people doing environmental cooperation. And this was all based on really an overview of this community-based research was based on Indigenous research methods coming out of the Mohawk-Akwesasne Reservation or community. Mohawk is another nation within the Haudenosaunee Confederacy. And so I followed and looking for protocols on how to actually engage in this kind of work. I looked towards existing Indigenous methodologies for cooperation, which kind of followed this three-part flow of building peace, developing equity or through a good mind, and then developing ways of creating empowerment, ultimately with the goal of sharing resources and justice is the ultimate goal of this kind of work. This manifested into a three-part workshop series, which I'll show you some pictures, but we did some tree walks and tree identification and learning about different stories of people's relationships with nut trees on the reservation. We had nut processing workshops where we actually took nuts that I and other people harvested and we made foods out of them using both contemporary and traditional methods and recipes. And then we also planted a lot of trees gave away a lot of seedlings to folks out on the res, but also planted there there's a school on the nation lands that we planted a lot of plants on. So just here's some pictures of the first part of our event, doing some tours. There's a business out there that made some custom shirts for us, which was really fun. We black walnut tie-dyed them, and this, I don't know the name, Decline. Okay. we made some cookies, and this is a homemade nutcracker that one of the nation members just like welded himself because that's what he was interested in. And here's a traditional corn pounder that we're using for busting up hickory nuts. And then we also did lots of plantings where we, a lot of these plants were either grown by myself or collected donation from local nurseries. These were mostly native nut and fruit trees, but also we had medicinal plants. Yeah, and here's some planting on the school grounds. And then, so that was chapters 1 and 5 I just showed you. And now this is chapter 2 or 3, I forget exactly the exact order. I did in a kind of a different direction, but worked with contemporary peoples. I conducted based on an observation that I was making in my field that a lot of other kinds of farmers, not necessarily indigenous peoples, but are really have been kind of taking up and really interested in growing nut trees. This has been something that's been happening in this area for over 100 years, but there seems to be a very recent, more invigorated interest. And so I wanted to actually put some numbers to this. There hasn't been really a quantitative study of who are growing nuts in New York and how they're doing it and why. So that is what I did. I developed a survey. And not only did I want to figure out who were growing nuts, but also how are they in relationship to cooperative extension. So these are, extension educators who are in many ways responsible for helping provide education and services to these growers. How well prepared are extension for this new, what seems like a new wave of a specialty crop in the state? And also I was really curious, how do farmers who aren't growing nuts, who are growing other things, what do they think about nut growing? What do people think about nuts? And so part of this is based in a literature review, and I did a lot of historical work learning about the history of nut growing in New York, as well as conducting a quantitative and qualitative survey of both of commercial nut growers. So I'm not really, in the past, it's really been focused on hobbyists and backyard growers, and really interested in who's folks who are growing these as a commercial crop. Farmers across other kinds of sectors in the agricultural industry, and then also educators. I'm gonna share some of those results a little bit later, but I really wanna go into the main thing. So that's, I was just kind of giving some overview of my previous work. My 4th chapter is very solidly an agricultural field experiment that was conducted in Varna, New York, where I grew hybrid hazelnuts, and looking at the way that different kinds of management variables during orchard establishment in years 1 through 3 affected plant growth. Pretty basic. It wasn't really about measuring yield or anything like that, but we were looking at 2 different genotypes, 2 different ground fertility regimes, and then 4 different ground cover regimes. This is a picture from the plot. I'll show you a little bit. So these were all my treatments. I had 16 different treatment combinations. So we use seedlings and clones, use of manure, composted manure or not, and then 4 different kinds of ground cover management, either a cover crop, black plastic as like a weed mat, unmanaged, or an herbicide treatment. And so each individual plot looked like, within each one of these treatment combinations, there were 4 plants planted as 4 replicates of the same treatment. And then this is all 16 treatments. And then each of the 16 treatments were then surrounded by a border row, so that none of the trees were considered on the border. They're all inside. So this is for statistical considerations. And then this was, I had 4 replicates of the entire, this entire set of treatment combinations across the whole field. So each treatment was replicated 4 times within a plot, but then also 4 times across the field. And the reason why I did this quadruplet replication was because then in each year, I wanted to measure plant growth. I did a destructive harvest, so I'd actually excavate each plant. So in year 1, 1 plant would be excavated, then another one, and then another one. And so then in the last year, there was just 1 tree remaining, which is why that's why I designed it this way. And the study area, it's a weird maps, but it's right here in New York, just a couple miles from campus. You could see my plot from Google Maps, at least as long as those, I'm sure next year they'll update the maps, they won't be there anymore. But yeah, that was cool to see. And I did base this all on allometric measurements. So this is plant height and stem diameter. There's gonna be a lot of nut jokes in here, so just get ready for the puns. And then also the destructive harvests. So this is just showing you some different examples of the work it took to actually dig up these plants, especially in the last year. In the early years, it was very easy, but then as the plants grew, we really had to chase roots because we wanted to get that root biomass. And so sometimes you have a plant that just looked very innocent like this, and then you'd find the root and you'd realize it just kept on going. It's kind of a little hard to see, but it just kept on going. Took a lot of work to get just one plant out of the ground, and then we just kind of shoved all these in the back of a car to bring them back to the orchards, where then I cut the plants up into pieces and ground them into powder so that I can measure the carbon and nitrogen in their tissues. So this is a very important part of this design, because this is the only way to measure how much carbon and how much biomass is in a plant, but it's also a huge limitation because the plants, these were only 3 years old, and this was a tremendous amount of work, and I wasn't able to actually, as you'll see, I'll show some of the results, wasn't able to do this for all the plants that I wanted to. So there were some limitations in the data because of the amount of, and also you don't know how much of the roots you're not getting. It's one of the really big issues in doing root biomass research is there is this unknown, unless you grow them in pots, but of course then it's not real soil, and the plants are bound in pots, so they're going to behave differently. So it's very challenging to, this is just one. So if anyone's really interested in solving some research challenges, we'd love to have your ideas on how to better study root architecture, root mass. Here is a figure of some of our main effects. So each one of these vertical bars is a different year of the study. So one thing that's very striking is that you really don't see the treatment effects don't really just show themselves until year 3. Year 3 is when we really start seeing these plants start to do something. These plants were planted as just as seedlings or clones from year 1. And you can also see the effects of where I wasn't able to sample something. So for instance, I was only able to dig up the roots. So this is a root mass here in this. So this is the bottom panel, the bottom horizontal panel, it's all the stem mass. Then this is, sorry, this is a little bit out of order, but stem is on the bottom, roots are on the top. And that's not the way it is in nature, but that's the way it is here. And then this is the combination root and shoot combined in the middle. And so I was only able to get root biomass I only chose one for clones, the clone plant material. And so that's just showing you a little bit of limitation in the data, but a way that I tried to, well, I'll get to that story a little bit, but one of the main stories in this is if you combine the plant material, so just like average together the values for roots, for clones and seedlings, like take that out as a factor, what we see is that our ground cover managements that eliminate weeds are the ones that result in the most plant growth by year 3. It's not a very shocking result, but it is very, I think that the magnitude of difference is pretty wild here. And we found that a black plastic mulch led to qualitatively the highest plant growth, not statistically different from herbicide treatment. So there's probably other things that we can do to manage weeds that are either black plastic had some management issues, and herbicide, if you're growing organic, that's not going to be an issue or not going to be an option. So there's probably other kinds of weed management techniques that could be worked out, studied here. I had high hopes for the cover crop, but I think I used the wrong mix of seeds, and I ended up using a cover crop that was actually deleterious to the plant growth. So that's also really important. Not all cover crops are created equal, and you want to make sure that you're really choosing your cover crop to match the kind of plant system you're working with. But one thing I really want to try to do, because I had this issue where I was missing data points, I wanted to see if I could use what data I did have and build models to be able to predict values where I wasn't able to observe them. So a lot of my work, I kind of dipped my toe into modeling. I didn't expect this at the beginning, but that's kind of where research takes you sometime. And so this is just a relationship of observed values between stem biomass and root biomass. And so we have a really, really great linear fit here. Um, but I wasn't, this only, if I were to, I could use this to predict root biomass from stem biomass values pretty reliably, but there wasn't that many data points. And so I wanted to know if I could use another measurement that I took that I had more data points of to predict as a proxy for stem biomass, then predict root biomass, kind of a two-step prediction. And what I found was that the basal diameter was a really good predictor of this mass of the above ground portion of the plant if you took the natural log of both sides. I have a lot more data points here and was able to find a really good fit. And so basically, if I took the log of the stem diameter, then I could predict stem biomass, which then I could use to predict root biomass. That's kind of a two-step process I took. And so I used values that I generated in this model to then impute them into this model. And then so I was able to build out my graphs using these predicted values. So all the red are clonal plant materials, blue are seedling, and then the all the bars outlined in dotted lines are those that I use the models for to predict. And so this was really, unfortunately, there's no way to verify this model because this is I'm showing data that I didn't collect. But this does show that the model, it does seem to be sensitive to the different treatment. So here on the x-axis, we have the different treatments, the ground cover treatments. So ground cover was the most significant treatment effect. And so we do see that the model is sensitive to the different treatments. Was able to predict that black plastic would have higher mean values than unmanaged or cover crop or even herbicide. So that was, that's basically the work that I did in this one chapter. So that kind of wraps up that one. And then the second chapter, I'm really going into depth here, is also really modeling heavy. And this is what the issue here is one of the, not only do these plants, chestnuts and hazelnuts, provide a really interesting food crop, but also there's lots of research and ideas about, well, if you are basing agriculture systems on trees, then trees are also taking carbon out of the atmosphere and putting them into very long-lived individuals. Chestnuts can live hundreds or thousands of years. There's a hypothesis that these kinds of systems could actually be used to mitigate climate change, to absorb excess carbon dioxide in the atmosphere, store them into plant biomass, even soil carbon pools, and that we can use these as a way of not only adapting agriculture to more environmentally friendly methods, but also really reducing our exposure to greenhouse gases by sequestering this carbon. And so I want to create an equation that could predict how much carbon is in a chestnut tree of any age. That was the point of this study. And so this was based on these kinds of data points. It took trees that were ages 2 through 80. And where possible, I collected the entire plant biomass above and below ground, and that was really only possible in years 2 through 3. And so years 2 and 3 were grown in pots and also in the field, and I was able to uproot, measure the entire parts of the plant. And all the other ones came from existing plantings. So we went out to farm fields and asked if they had trees that they were going to thin out anyway that we could pay them for or if they were not going to already thin out this tree, if we could pay them to remove this tree would, it'd be like it's lost, possibly a lost crop for them. So I was able to get, as much as we could. We were able to find an 80-year-old tree. And so I can show you a little bit about, so this is what the sugar harvest looks like on the over here, washing off roots in the pot grown ones. And then here we actually went out to farms, and that was Marvin. This was at an 80-year-old chestnut planting in Montour Falls. where we cut down the whole tree. We strip all the leaves off, break the branches into pieces, weigh them, measure all the leaves, and then take samples of them and measure them for the carbon content. So this is a summary table of all my data. Up here, we've got, these are the allometric measurements of diameter and height of the different plants. So you can see I have a lot of plants that are age 2. And as the plants get older, it's harder and harder to find individuals. And that's another one of the limitations of the study, but it's also just, there's not many 80-year-old plantings to sample from. It's also the limitations of this field of agriculture. And this kind of work. So we really need more long-term, if we want to understand, this is really a first pass. And this is, I'll show you more about the equations I created, but they are the first allometric measurements made for chestnut trees in this way, based off of biomass. Other ones are really based off of just the diameter and height and branching patterns. So we need more long-term studies so we can verify and further make these models more robust. But yeah, it took diameter, heights. We have carbon contents of root stems and leaves. This middle panel is just the biomass of the plants in kilograms. And then down here we have the biomass of the carbon content. So just the carbon content. So it's this percentage multiplied by this mass gives you this is the actual grams or kilograms of carbon in the plant tissues. So an 80-year-old tree, the one that we've measured at least is about 600 kilograms, and just under half of that is pure carbon, biomass carbon. Another part of this is that we wanted to capture how yield played into this, because plants, that's part of mass too, and that's also part of the carbon. Carbon goes into the plants. And so in order to do this, I did a literature review from all existing literature, some of it actually unpublished across the world, because chestnuts are grown all across the world. This is also perhaps the first meta-analysis of chestnut yields. So this is also, all of these data points are built into the model as well for predicting yield. And there's still a lot of variability. The chestnut industry is still very nascent, and we are finding which cultivars do best where. And so that's why there's a huge spread of data. And of course, too, there's lots of different locations while these are grown, which is going to affect the yields. So one of the issues I found was that when I tried to look at how diameter affected the mass of the stem, so the above ground biomass, looking at these very simple comparisons, we do not have linear relationships, right, at all. We have little growth for a long time, and then it kind of shoots up. And if you plot the residuals, you get some really weird stuff that kind of obliterates any of the assumptions of linear modeling. This is very frustrating. And so I had to do a lot of work playing on all different kinds of transformations. So here again is that same relationship, diameter of the stem to the diameter of the stem to the mass of the stem. This is all untransformed. If we took the natural log of the mass, it did something different. Kind of, we saw, but it's still not really suitable for a linear regression. If we instead did the natural log of the diameter, also a different effect, but not really useful for linear regression. And of course, the winning model is a natural log of both. And so looking at this is just my error plots and just kind of verifying that this linear model would work well, and it mostly does. And so we kind of went with taking natural log of both axes and going with that. And so, of course, one of the biggest issues again is being able to measure root biomass. And so one of the first models I built for this study was estimating root biomass based on that log-log linear relationship. So we found also all the red dots are observed root biomass, and then the blue dots are ones that the model predicted. So we are able to, with very satisfactory results, able to use this model to predict root biomass based on the natural log of stem diameter, which was like one of the best. The diameter to mass was one of the best diameter was the best predictor of mass, overall mass. And so yeah, these are basically the same curve, but one is for biomass carbon, as the other one is just for biomass. But of course, predicting the log of root mass is not that useful. We want to know what the root mass is in its original terms. So we had this nice log model, and now we have to back transform it into its original units to actually be of use. And so in order to do that, you just take the natural log, you raise that relationship to E, since it's a natural log. And so when we exponentiate our model, we get this really beautiful curve. And these are our error terms. We only have single data points out here, and this is at the extreme end of our model. So the error is, of course, going to be very large, and the error in the log transform space becomes an exponent. So that's also why we see it becomes an exponent in the linear space, which is why we see these huge error bars. But this is exciting. This is a first pass of a root biomass model based on diameter. But of course, the question was not how much carbon does this tree have based on its diameter? It was based on its age, and that required another kind of modeling. But after I was able to do those models, I was able to then impute these new values into this data set, and I was able to build out an estimation of the whole tree biomass using modeled root values, which is really exciting. And then I could create these really fun graphs. These are sigmoid curves that basically predict, based on tree age now, how much growth we have. So this is an equation for a carbon tree, a chestnut tree. And one of the limitations of this modeling approach is that the model I used assumes that the rate of change here at these ends are symmetrical. And they're probably not. It's probably much more likely that towards the trees, as the tree is reaching maturity, this shoulder is really going to be much more gradual than this exponential growth that's happening when the tree is really young. But this was the extent of my modeling abilities. I'm sure there are more. Maybe if we got more data points, we could fit a closer model. Yeah, and then so this is it's the same formula, just slightly different numbers for the carbon content. So then, over 40 years, so a tree seems to stabilize its growth, kind of plateau at about 40 years, according to this study. And so averaged over those 40 years, the chestnut tree, one single tree, tends to accumulate 8 kilograms of carbon per year. And if we put this into some perspective about, 250 trees per hectare is about 100 trees per acre. And that is a common planting density, which would create 2 tons of carbon per hectare, which is equivalent to 7.4 tons of carbon dioxide equivalents per hectare per year. So that is according to this model, based on actual mass measurements, that is the carbon sequestration potential of a chestnut planting. And to put this into some context, in New York State has about, I think, 7.4 million acres of land, and 1 million acres of that are agricultural land. 1 million acres in total are underutilized, so to speak. And only like 26% of this is, the reason I'm talking about marginal land is because these chestnut trees are, they're still not a mainstream crop. So people are probably not going to be like tearing out soybean fields and corn fields and planting wholesale to chestnut trees. But the chestnut trees do really, really well on sloped land, on land that's very acidic, land that's very rocky. And so marginal land is actually a really great opportunity to add to our agricultural portfolio in ways that not only produce food, but also provide a climate benefit. And so this is the total, this is the quote unquote marginal land in New York, and 26 of it is like readily available for activation, for improvement. So if we took, of this 1 million acres, just 26% of it and planted that to chestnuts, that's equal to about 105,000 hectares, or and at this rate, we would be sequestering 210,000 tons of carbon per year, which is equal to almost 800,000 tons of CO2 equivalents. And to kind of put that into a grander perspective, we as a globe are looking to really sequester 11 gigatons. So this is a really far off. This is a 100th% of a gigaton, but this is really on just 26% of larger land. So while it may not make, this in and of itself is not going to make a dent in the world's global climate problem, it does objectively provide a piece of this pie. And New York alone, I mean, while we need 11 gigatons, agroforestry in and of itself across the globe has a potential to sequester up to 5.7 gigatons of carbon dioxide equivalent. But on the low range, it's 0.1. This is not super far off from 0.1 gigatons, but so just showing that even within a small portion of New York, we can actually see that agroforestry and planting these woody perennial crops really can start to help address the call for aligning agriculture with climate smart production, and carbon sequestration. Another aspect of this research was looking so the chestnut trees produce, these are the same sigmoid curves that are showing plant growth over age, but one thing that wasn't really well represented on the previous ones was that leaves and the actual chestnut yield, the burrs, the nuts, those get produced each year and go away. They're ephemeral, as opposed to, the wood accumulates every year. And so you can measure how much, when you measure a plant's stem at age 80, that is the accumulation of the biomass of that single tree over all those 80 years. But when you measure the leaves on that 80-year-old tree, you're just measuring that 1 year's growth. So we wanted to also see over the course of a tree's life, how much carbon has been going into those ephemeral products, the nuts as well as the leaves. And so here is a cumulative map or cumulative graph of those parts. So over an 80-year-old tree's life, it produces almost a ton of carbon in leaves alone. And this is important because this really impacts the soil carbon, especially the leaves. The carbon that does come from the yield does often get exported, at least the nuts. The chestnuts, they are a nut inside of a burr. The burr can stay in the land and get recycled back into the soil. Well, you do have an export of carbon and nutrients from, just from selling your product. But the leaves can be managed, and we can actually, this is not just something that goes away every week. It doesn't have to be something that goes away every year, but it actually can go and feed the soil. And that was, this gives a proxy or an idea to a pool of carbon that I was not able to measure in the study, which is in the soil itself. And to kind of look at some figures from other studies that show, unfortunately, this is covering some of the information, but what we do see is that in a similar chestnut planting that's been conducted over 24 years, is that organic carbon is much higher in the top 10 centimeters compared to a corn soybean rotation. And then it's about 15% higher. And we also see in another study, the agroforestry plantings, so not just necessarily chestnut trees, tend to at every soil layer have more carbon in the soil. There's other studies, these are other meta-analyses of showing carbon benefits to the soil from different kinds of agroforestry plantings. I don't have time, I don't think, to go over these in detail. And then this graph is showing, this is a heat map. These are all different kinds of other soil characteristics. This is just chestnut alone. This is double planted chestnut. This is chestnut and pawpaw, and this is pawpaw alone. So we see that adding in plant diversity, having two different kinds of trees, really increases the number of positive of benefits, which is another really important aspect of agroforestry, is not just having woody perennials that are not disturbing the soil and growing year after year. Thank you, Carlin. But also plant diversity also plays a really important part in other not just carbon, but other kinds of soil benefits that are really important. Really important. And when we have also, I should say that when we have organic matter concentrations, organic carbon concentrations greater than 2%, it's really important because that really talks about the amount that really is a sort of a factor that affects soil health, soil quality, the amount of nitrogen that's available. So more broadly across New York, so this is kind of going back to the survey research that I did. What is, I did all this quantitative work, but really what is the state of nut growing in New York? Why does this matter? What is the greater context? So in 2019 alone, we saw over almost 13,000 trees, chestnuts and hazelnut trees being planted across New York. And more than, and that was great. That was seven times greater than the number of trees planted in 2017. So in those 3 short years, seeing an exponential rise in the number of farms that are planting chestnuts and hazelnuts. And the majority of these have only started in 2016. So while nuts have been existed in the state for thousands of years and people have been growing them for hundreds of years, there's really, right now is a time of intense, really energetic interests in nut trees. And many of these farmers are identifying with organic, regenerative, diversified kinds of plantings that really bring together not just production agriculture, but also other kinds of ecosystem services and more ecological production methods. And all the ones I surveyed across the state intend to plant more nut trees. So this is not just, it doesn't seem like it's a passing fad. It really seems like these folks are really trying to build an industry. And what this looks like across the Northeast is there's actually quite a lot of activity. There's research institutions in the greater Eastern US. There's several nut cooperatives also in the Midwest area. And there's even one forming here. The New York Tree Crop Alliance is a nut tree cooperative that's happening, that's already established right here in New York. Here is a list or just a mapping of, these are all existing chestnut plantings that are currently bearing in New York. I'm in the process of visiting all these over the next few weeks. Last week I visited all of these. This week I'll be going to the Mid-Hudson and to the Albany area, meeting these growers, taking pictures, learning about their production methods. This work is being supported by a number of different grants. The USDA just injected $2.8 billion into something called climate smart commodities, of which nut trees are part of the several awarded proposals in that recent grant. This is a view from probably the largest chestnut orchard in New York State. I was just out there on Friday. This is just 12 acres, but about 12,000 plants. Really incredible place. And the IPCC recognized, that's the Intergovernmental Panel on Climate Change, recognizes the extreme importance and demonstrated benefits of agroforestry, but notes that there is a lack of institutional support in order to really ensure adequate management, but also that it's happening on the scale needed. So we really need places like Cornell University and other research institutions in the Northeast to continue doing this work. If you're interested, we need folks figuring out how to integrate these into diversified cropping systems like alley cropping and silvopasture. Really great need for breeding work to be done. there's so much has been planted out there. We need to figure out what is best and how to continue supporting these industries. There's new pests and diseases that are happening that we really need help with learning how to do better with and anticipate new ones. There's really great modeling work that can be done with climate mitigation, ecosystem services, and yeah, if you're interested in food science aspect, this is some other work that's happening around the country. And thank you so much for your time. Please get in touch. My contact information is here. I really appreciate your attention. Yes.
Okay, any questions?
Yes, Ken.
Regarding veolometry,
Yes.
was it based on Chinese chestnut, Castanea mollissima?
So mostly, definitely for the older ones, the young field-grown ones, those were European Japanese hybrids. But and then I think the 6-year one was a Japanese chestnut seedling. The 22-year-old one came from the Lansing planting that Ian Merwin did. That's Mollissima. And the 80-year-old was also Mollissima.
Just wondering,
Yeah.
the work that they're doing at Syracuse University to kind of restore the American chestnut. I would imagine they might have this sort of allometric data that you could compare to Mollissima. Compare American
Perhaps.
chestnut to Chinese
Yeah.
chestnut.
Yeah, that would be interesting. They have very different growth forms, and I've not asked them about that. Great question. Yes.
Samantha,
Yes.
John,
Thank you.
I was interested in your video where you showed all the trees planted out. They seem very large and very far apart. Is that just historical? That's how we've always done it? Or was anybody looking at trying to be a little bit more intensive in terms of planting?
Yes, those are seedlings. They're growing on their own roots. There's not like dwarfing rootstocks for chestnuts. Grafting is a huge issue in chestnut. Most grafts fail. And so that's just the nature of the plantings, that they're large. That offers really good climate benefits because it allows the trees to grow to the full size. So they're able to store all that carbon. But that's currently the planting density. Because if you plant them any denser, I mean, those also were not at full maturity. Those are all at about 10, 12 years old. We saw the plants are not really going to finish growing until 40. So.
Right, but there seems to be some sort of, in a way, conflict is not the right word, but that on one hand, you're dealing with perhaps a yield type system, like apple trees grow for 50, 60, 100 years.
Right.
But nobody grows to that, right?
Mm-hmm.
Because they're focused on the yield of the nuts. On the other hand, you're focused on carbon sequestration. So, which one is more important?
Mm.
I'm just curious.
Yeah, well, I think the goal is not to say which one is more important, but how can we leverage the both? Because the idea is that farmers might be able to get paid for the carbon benefits that they're bringing. So we want to be able to bring the most yield, but also the most carbon stored. That could potentially be a double source of income for these growers, because not only are they producing a saleable crop, but they're also doing a social good for the globe. Yeah.
I think we're on time. Do you have a quick one?
Yeah, I've got a quick one. So I just had a question about I think you looked at the sigmoid model,
Yeah.
and kind of like the potential biological impact of that. So is that just because that's how the model is there a point further off the x-axis in which that stops making sense in terms of tree age, and then the y-axis was the carbon sequestration
You mean there's a point where it declines?
Right, because it pretty much levels off at some point in age. And so is that is there a biological basis to that leveling off where the trees really turn 80 and kind of stop putting on new growth?
Well, it's not so much that they don't put on new growth, but it balances with how much dies. So there's no net new growth.
Okay,
Yeah.
cool. Thank you.
Thank you very, very
Yeah, you're
much.
welcome.
This has been a production of Cornell University, on the web at cornell.edu.